Well, right after learning the product rule, we should learn about the quotient rule as well. So with the quotient rule, we're trying to find the derivative of a function that's the quotient of two other functions. So we start with our definition of the derivative. The limit as delta x approaches 0 of f over g x plus delta x minus f over g of x, all divided by delta x. So the first thing I want to do is just a little rearranging. To get rid of the fractions inside of fractions, I took this denominator and pulled it out as 1 over delta x. Then, using the definition of f over g of x plus delta x and f over g of x, wrote them as their two fractions, right here and right here. Next, I want to subtract those two fractions. And in order to do that, we need to get common denominators, which means this first fraction is going to have to get multiplied by g of x over g of x. And the second fraction has to get multiplied by g of x plus delta x over g of x plus delta x. Doing so, we end up with our expression looking like this. Next, I'm going to want to do some rearranging. The first thing that I want to do is to get rid of this fraction that's out in front and instead bring that delta x into the denominator. The other thing I want to do is make some room. I'm going to scooch this stuff way over so that I can do a little bit of a math trick. What I'm going to do is I'm going to subtract f of x times g of x. And then I'm going to add it right back in there. So f of x plus g of x. So overall, I haven't changed really anything. Next, I'm going to do a little bit of rearranging. I'm going to pull this product out in front in the same way that I did in the beginning with that delta x. And then I'm going to split my fraction into two separate fractions, the sum of two fractions. And we end up with this expression here. Notice that there's that g of x plus delta x times g of x. And then my two fractions, that got split up. My first fraction has this as our numerator. And the second fraction has this one as our numerator. Now, I notice that in each of these fractions, I have a common factor. So, in the first fraction, that common factor is g of x. I'm going to take that and factor that out in front of this fraction, right here. And I'll be left with f of x plus delta x minus f of x over delta x. And that's something that should be very familiar. In the second fraction, my common factor is this f of x. So I'm going to do the same thing. Pull that out in front of this fraction. And I'm left with g of x minus g of x plus delta x over delta x, which is familiar, but not quite right. We need to have that x plus delta x be the first term in that numerator. So in order to switch that order of subtraction, I'm going to factor out a -1 as well. Then the last thing I'm going to do is take this entire set of parentheses that I have here and put that in the numerator of this fraction. It looks like a big mess, but let's kind of see that happen again. That in my first fraction, I factored out my two g of x's out in front, and there they are. In my second fraction, I factored out those two f of x's right here. But I had to switch the order from g of x minus g of x plus delta x to g of x plus delta x minus g of x. And that made my plus turn into a minus. Then I put that entire thing in the numerator of this first fraction. So that's where it got set up here. Now we're ready to take the limit of this. So let's see what we get. As we go through our fraction, piece by piece, we're going to let delta x approach 0. G of x doesn't have any delta x's in it, so it's going to stay g of x. this fraction, as delta x approaches 0, f of x plus delta x minus f of x over delta x is our derivative of f of x. In the next term, that f of x doesn't have a delta x in it, so it's going to stay minus f of x. And when we look at our fraction, as delta x approaches 0, that fraction is going to be our derivative of g of x. And in the denominator, we have this only one delta x in there. That's going to approach 0. So we'll have g of x times g of x, which is g of x squared. So maybe looking at it in terms of Newton's prime notation might look a little bit nicer, a little less messy. But the idea is still the same. We have this fraction in the numerator. It's g of x times f prime of x minus f of x times g prime of x all over g of x squared. Now that gets messy, and we are going to have to memorize that one as well. So one way to kind of help this, what you can say to yourself instead of g's and f's primes and all that, I was always told this saying: low d high minus high d low over the square of what's below. Low d high minus high d low over the square of what's below. Notice that we started with a fraction. Numerator was f of x, denominator was g of x. When we find that derivative, we're going with the denominator times the derivative of the numerator, minus high d low, the numerator, times the derivative of the denominator, over the square of what's below. So over the square of the denominator. All right, so let's get some practice using the quotient rule. Find the derivative of f of x equals 5x minus 2 over x squared minus 1. So when we find the derivative, we're going to go low d high minus high d low over the square of what's below. So my low is the x squared minus 1. D high, the derivative of what's on top is 5. So low d high minus high d low. So 5x minus 2 times the derivative of the denominator. So derivative of x squared minus 1 is 2x over the square of what's below. So take that x squared minus 1 and square that. Now, when we simplify this, what we're really going to do is kind of just clean up the numerator quite a bit. But I'm going to leave that denominator as x squared minus 1 squared. We'll be left with 5x squared minus 5 and minus 10x squared plus 4x. When we clean that up, 5x squared minus 10x squared is negative 5x squared plus 4x minus 5. All over that x squared minus 1 squared. And that's going to be good. If you wanted to expand the denominator, of course, you could. Basically, we want to kind of clean things up so that they're usable, but not go through so much of the simplification process that we take up a lot of time or possibly make some silly mistakes. So how about when g of x is equal to the natural log of x over square root of x? When we want to find that derivative, we're going to go low d high minus high d low over the square of what's below. So my low, my denominator, is square root of x, times the derivative of the numerator, natural log of x, which is 1 over x. Low d high minus high d low. So the numerator times the derivative of square root of x, which is 1/2 x to the negative 1/2 power. Over the square of what's below. So we'll have that x, square root of x squared. And now we should clean it up a little bit. for the numerator there, square root of x over x. And the next term, natural log, will be in our numerator, and our denominator will have 2 square root of x in it. And then over square root of x squared, just being x. So instead of leaving the fraction inside the fraction, what I'm going to do is take our numerator, instead of dividing by x, I'm going to multiply by 1 over x. And that'll get rid of the fractions inside of a fraction. So we'll be left with square root of x over x squared minus natural log of x over 2x square root of x. And again, there is more simplification you could do if you wanted to, but this looks clean enough to be very usable. We can also use the quotient rule to help us find derivatives of other trig functions. We know that the derivative of sine is cosine and the derivative of cosine is negative sine, but what about tangent? The important thing is to look at tangent as a quotient. Tangent is sine over cosine. So when we want to find the derivative of that, we just use our quotient rule. Low d high minus high d low over the square of what's below. So my low is cosine. Derivative of the high, derivative of sine is cosine. Low d high minus high d low. So minus sine over the derivative of cosine, which is negative sine, over the square of what's below. So over cosine squared. Now when we simplify that numerator, we have cosine squared minus sine times negative sine is plus sine squared, all over cosine squared. And we have that identity that cosine squared plus sine squared is just 1. So 1 over cosine squared. And if we want to get rid of the fraction, the reciprocal of cosine is secant. So the derivative of tangent is secant squared. What about the derivative of secant then? Look at it in terms of cosine, that this is 1 over cosine. Then we can use our quotient rule. Low d high minus high d low. So low is cosine. Derivative of 1 is 0. So low d high minus high d low. So my numerator is 1. And derivative of cosine is negative sine over the square of what's below. So over cosine squared. When we clean this up, my first term is 0. So I'm just left with sine in the numerator and cosine squared in the denominator. I'm going to break that up as cosine times cosine, because I want to get rid of the fractions. So I'm going to write this as a product of 1 over cosine times sine over cosine, and the reciprocal identity says this will be secant times tangent. So the derivative of secant is secant tangent. When it comes to finding the derivative of cotangent and cosecant, they're going to be done in very similar ways, but they're left as part of your homework assignments. But that is the quotient rule.